right, so let's get started with Chapter 4, Section 3, Numerical Methods for Systems of Differential Equations, First-Order Differential Equations. And I want to review some learning outcomes for today's lesson. So at the end of this lesson, a student should be able to do the following. Set up a system of differential equations to be solved numerically. We're also going to review Euler's method, improved Euler's method, and the run-cutted method for numerically solving differential equations. We're going to actually use Maple to solve a system of first-order differential equations numerically. And we're also going to be using a feature of Maple called ODE plot so that we can graph information that we get from solving the differential equation using the dsolve command numerically. All right, so let's get started. So we first start out with our differential equation. We have a kind of a column vector of derivatives, and it's equal to another column vector of functions of f of t, where these functions could be a function of t and the column vector x, where x contains up to n variables, and the derivative of with respect to x contains up to n variables. So that's where our system is. And we're going to have a column vector of initial conditions for a specific value of t. We'll call it, should be t0. They're going to be another column vector of initial conditions, x0. And so a column vector looks like this for a system of three equations. So I've got x1, x2, x3. And then I'll have functions f1, f2, and f3. And then using Euler's method, I want to take my present value, initial value of column vectors, multiply it by my step size, and multiply it by evaluating our functions at t of n and x of n. And then if we're going to do improved Euler's method, I'm going to make a prediction of what my next spot should be using Euler's method, we just did above. And then I'm going to take that prediction and plug it back into the function at my future step of tn plus 1, which is tn plus h, and what my past location was, and average those two and multiply it by h. And that'll give me my future prediction for my column vector x. All right, so we can do the same thing for the run-cutted method. It's just that we have more k's. So our future prediction, again, is I'm going to predict 4 different slopes for my differential equation. We call them k1, k2, k3, and k4. And these will also be column vectors. And then I'm going to weight them and average them and then multiply by my h to get my future location. So K1 is evaluating everything at my present, my function at my present location. K2 is I go half a step size into the future and evaluate my future values of my column vectors using my slope K1. My next step, K3, is the same thing, another half a step into the future. Again, making another prediction of what my future location should be in my column vector, but this time using my slope from K2. And then K4, I make a full time step into the future and evaluate a full time step into the future what my predicted value of x should be. In this case, my slope I'm using is K3 from the one I had before. And what we're going to do is try to solve this problem using these numerical methods. So I'm going to use Maple to do this, but it says you can use a handheld calculator, and there's a program in the book you can program into your calculator. But the first thing we're going to do is we want to get to x 0.2, where t is at 0.2 for x and for y, using Euler's method of step size of 0.1, using improved Euler's method of step size of 0.2, and then using the Runcutter method at step size of 0.2. And then compare our approximate values to the actual values of the function at those points. So the functions we're going to solve are these differential equations. I have these initial conditions, and it even gives me my predicted, my actual solution for this system of differential equations. So what we're going to do now is switch to Maple, and I will show you how to do this in Maple.
Okay, so let's talk about these numerical methods for systems of equations. So we're going to be solving equation 1 on page 256. So here is what the derivative of x should be equal to, and here is what the derivative of y should be equal to. I call these equation 1 and equation 2. Alright, so what we need to do is set up our initial conditions. So the problem states that x at t equals 0 needs to be 0, and y at t equals 0 needs to be 2. I need to make sure that Maple knows all these things. So I'm going to hit return. And then the restart command to clear out memory. And set equation 2. Let's set our initial conditions. And then the time starts at t equals 0. I want my step size to be 0.1. So, and it tells us we want to find our values of x and y at t equals 0.2. And then I get my number of steps. So I have 2 steps. So I need to create my 2 functions. So f is going to be able to solve for my derivative of y. Now, how do I do this? Well, I have the function stored here. The function commands stored here. This is the 2 variable one that I'm using here. Let's see. I believe you can find these in expressions. Here they are down here in expressions, right here. You see that right there? Alright, so let's execute my functions. There's my f and my g. Now I'm going to do my time steps. So you type in your for loop. Now here's the trick. When you hit this, you don't want to hit enter. You want to hit shift enter. And that'll drop you down to this line. And then you type this line in. And this is Euler's method. Euler's method for finding x. So my present x plus h times evaluate my function at x and y, at present x and y, and then my y is right here. Now you need a colon at the end of this line, and again another shift enter, a colon and another shift enter here too. So, and then I'm going to increase my time by h, another colon and a shift enter, and then I want to print out all the information here. So I'm printing out my value of t, x, y, and my exact solution that they give us in this problem for both x and y, and then I can compare it. And then another shift enter, but the last one's a semicolon right here. And then you type and do. You see how this is bold, and then a colon, and then what you want to do is hit enter. And there is our solutions. So if we look at our answer, our x is the same value to 1 decimal place, and our y is the same value to 1 decimal place of the exact solution. This is the exact for x and the exact for y. So x's and the exact y and these are my numerical x's and my numerical y's. This would be x of n, and this would be x of y of n. And see all the way at the bottom, I'm off by more than a decimal place down here. And then my y is much more accurate. I mean, evaluated is to at least the first decimal place. Alright, so that finishes the Euler's method. Let's go. Alright, so that is Euler's method. Let's look at improved Euler's method now. Improved Euler's method over the same problem. Okay, so I got the wrong page numbers here. So let's fix that. Okay. So if I open up improved Euler's method and click restart, and then same equation, equation 1, equation 2, same initial conditions, same start time, same step size, same end time. This should be t. Same. Alright, so I believe it's not the same step size. I'm going by steps of 0.2 spaces, so it's only going to be one time step. Same function of x, for the derivative of x, same function for the derivative of y. What's going to change is the algorithm we're using to find our Euler's method. Okay, so I have two Euler's methods I have to find. I have to find Euler's method for x and Euler's method, improved Euler's method for y. So I have my u, and then I also have this v, and that's my guess at my future step for y, and my u is my guess for my future step for x. So I evaluate that using Euler's method, using the present x and y values that we have for my function f and my function g, and then I take that value for x and y and I plug it back into here, and then I evaluate my functions of f, multiply it by h divided by 2, and then I evaluate my function of g, multiply it by h divided by 2, and then add my present x and my present y, and then I increase it. Now again, when you do this for statement and execute this, when you got to hit shift enter here, 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 and then semicolon instead of a colon, and shift enter here. And this line prints out everything that we do. So if I come up here and hit enter, we get our answer. So we can see that our x value is a little bit closer to the exact than it was before, and our y value is a little bit closer there. Not exactly perfect because they are numerical methods and there's error involved in that. So that shows you how to do your numerical method in for improved Euler's method. Let's move on to the run-kutta method. Alright, so I'm going to hit enter here. Same function for the derivative of x, same function for the derivative of y. Starting x, starting y, starting time step is going to be 0.2. I'm going to stop at 0.2 times 0.2. Let's make this t, it should be, and then hit return. I'm going to do one time step, create my functions now again. Alright, so here's the completely different one. Our for loop in here has all these k's, and I have k1s and k2s because I have different functions to evaluate. I have k1x's and k1y's. So k1x is evaluating my derivative, my function for my derivative of x, and the k1y's are evaluating my derivative for y's. Okay? So we do this with the same strategy we had before in Runkutta. So I evaluate my slopes of my solution functions at the present x and y, and those are my k1s. I evaluate my second slopes by advancing a half a time step into the future for x and for y, using the slopes I just calculated for my k1s. And then I do the same for my y variables. You see that these are the same functions that I used for k2x and k2y for evaluating what x of n plus a half should be and y of n plus a half should be. And then I do my k3s, and that's the same strategy we did for k2s, except I replaced my k1s with my new slopes that I calculated, my k2s. Right here. And you'll notice that I evaluate my x's the same way for this. And I evaluate my y's the same way. Alright, so then we go on to K4s, and the difference between the K4s is I go a full time step. So I go a full h, and then I use my slope of K3s that I calculated before, so a full time step of h. And then again, I use the same values for my x functions, and the same value for my y functions. And then I have to predict my future location for x's. And again, I take a weighted values for my slopes for my x's, and then I multiply them by h and divide by 1/6, and that gives me my new prediction for x. And I can do the same thing for my slopes for my y's. Multiply by h, divide by 6, and that gives me my future value for y, and then I go my future value for time step. Again, at all these points here, when I put the colon in, I have to hit shift enter. All these have to have shift enter to stay within this for loop. If you don't do shift enter, it's going to be pushed outside the for loop. And then I have this print line that prints out my t value, my x of n value, my y of n value, my exact solution for x, and my exact solution for y, and that's given in the problem. Alright, so what does this come out to be? Let me hit enter. Alright, there's my answer. Okay, so now if we look at this, you'll notice that my x of n value right here is within 2 decimal places accurate to my exact value, and my y value right here is accurate to 3 decimal places. Alright, so that's how you do the improved Euler's, the Euler's method and the Runkutta method for solving a system of equations numerically.
One of the other problems we're going to do using some different features in Maple is our spacecraft landing, and this is part of the applications manual you're going to have to use, and the problem is stated this way. Your spacecraft is traveling at a constant velocity v, approaching a distant Earth-like planet of mass m and radius r. When activate your deceleration system containing a constant thrust t until impact with the surface of the planet. During the period of deceleration, your distance x of t from the center of the planet satisfies this differential equation. So this is a second order nonlinear differential equation where t is our thrust, g is a universal gravitational constant, and m is the mass of the planet. And x, or x of t, is the distance from the center of the planet to our spacecraft. All right, so what is m going to be r, and how are we going to find our constant thrust, our constant velocity, or I should say our initial velocity v, and our thrust factor t? Well, m is given there in kilograms, r is given there in meters, and I'm going to give you our thrust in kilometers per hour. I think it would be better to put that in meters per second. We'll talk about that later. But P is determined by your student ID number, and then this Q in the thrust equation is also determined by your student ID number. And G will be the acceleration due to gravity of R. I don't think it's the acceleration due to gravity of the planet, but it's going to be determined from the mass of our planet and some variables there, and we'll get into that when we solve our problem. So here's how we find little g. It is going to be the gravitational constant times our mass of our planet divided by the radius of the planet squared. And then I've also written in what the value of the gravitational constant is going to be, but you can get all this from the book. And now you choose P to be your smallest non-zero digit in your student ID number, and Q is your next smallest non-zero digit in your student ID number. And then what we want to do, the whole idea is to find the ignition altitude, or the distance above the planet. We have to engage our thrusters to slow us down, and we want to calculate that to our nearest meter, and we also want to get the resulting descent time into the nearest tenth of a second. Okay, so how do we set this up? Well, we have a second order differential equation. So the first idea is to make it a first order differential equation, or a system of that. And so what I'm going to claim is the first derivative of x with respect to time is going to be equal to w. That allows me to claim that the first derivative of w is equal to the second derivative of x with respect to time. And if I put that back in, I get this expression in the first derivative of w is equal to that. So what I have now are my two equations. That's going to be one, and this is going to be another. And so we're going to do this using the run-kutta method, because I think this is most accurate. So we're going to need a t, an x position for the distance from the center of the planet, k1, or that's the slope of our function, and this first differential equation evaluated at tn xn. This is going to be our second calculation for our slope per run-kutta, our third calculation for our slope per run-kutta, and our fourth calculation for our slope per run-kutta, all using this and this differential equation. And then the g's are going to be our calculations of our slope for this differential equation over here. So the g's here are associated with this calculation of the slope, and are k's here are associated with this calculation for our slope. All right, so how are we going to do this? We have to calculate k1. Well, that's going to be technically our velocity, or in our case, our first one should be our initial velocity v0, and then our k2 is going to approximate v0 by calculating 1/2 a time step into the future, and our first slope for here, because this is our slope of w, and that's how we calculate it. So I'll have to evaluate this at locations of x at 1 time step into the future, or 1/2 a time step into the future. And we'll be showing you this in the code. And so then our k is done the same way, except I'm going to use my g2 value for approximating the slope of the velocity to get my slope k2. And this is going to be my k value, or my fourth value, k4. Again, I use g3 to calculate my slope and my velocity. And then we'll weight them together, add them, add them, multiply by h, divide by 6, and that'll give us an approximation for how x is changed. And then how do we figure out how w is changing, which is technically our velocity, and this is our initial velocity here. And we still got our same differential equations, but then this is g, so g1 would just be our first position of x. Now g2, I'm going to have to use my second approximation for x, so I have to go back and get my k1. And then g3, I have to use my third approximation for x, so I have to go back and get k2. And g4, I'm using my fourth approximation for the change in x, and that I have to go back there. And this gives me my g1s, my g2s, my g3s, and my g4s. And again, I'm going to weight them, add them, multiply by h, divide by 6, and that'll give me my prediction of what my velocity should be at my next step down here. Okay.
All right, so your applications manual has several problems it wants you to solve. One of them is called the spacecraft landing. So we have several constants and parameters we need to set up. So we're going to do that in Maple. Okay, so if I hit return, I'm going to clear out my memory, and then I'm going to define my G, or my universal gravitational constant, and then they give you the mass of this Earth-like planet. I'm just going to call the mass of the Earth because it is the mass of the Earth, and the mass and the radius of the Earth because it's the radius of the Earth. And you have to define numbers from your student ID, and this is my lowest non-zero number in my student ID. And then this is my second lowest number in my student ID, and that's my P's and Q's. You define your initial velocity of the spacecraft by multiplying P times 10 to the 4, and then they have it in kilometers per second, or kilometers per hour, and I believe we need it in meters per second. So that's what the 1,000 is. There's 1,000 meters per 1 kilometer, and there is 3,600 seconds in an hour. So I've plug in that and hit return. Now, I've also put in a minus sign, and I think the textbook misses that. This velocity needs to be minus to start out, or else you're going to be moving away from the planet and you want to be going towards the planet. I have positive is pointing up. Alright, so I'm going to hit return there. And then you need this little g, which is the acceleration due to the force of gravity. And we calculate that by big G times m divided by r squared. And then our thrust vector, or our thrust from a constant thrust from the spacecraft, that's what we're going to be using. And then we have to solve our differential equation, just like I showed you earlier. I have equation 1, so the rate of change of position x1 is equal to x2, and the rate of change of x2 is equal to our basically our function that we have, because this is the second derivative of x, and then I need to square x1, and it has a function of time, so I'm going to hit return there too. Okay, so this is our first derivative we're solving, and this is our second derivative we're solving. Alright, so the big question is this number right here. This is our initial guess for what we start at, and I'm going to go 2 times r, which r is the radius of the planet to start out with, and then hit return. And then that's going to set up our system of equations, right? So I've got my first derivative, first order differential equation, my second first order differential equation, my initial condition for the first one, and then my initial condition for the second one. Now here comes the new stuff. I am going to invoke this desolve command, and the desolve command has to be done this way. So I have a curly bracket, equation 1, equation 2, initial condition. Okay, so here is our desolve command that we want to use. So I'm going to put in a curly bracket, and then my first equation, my second equation, my initial condition, and then this initial condition I'm going to start out as being 2 times the radius of the planet, to see if that works, because this is the trick. They want you to find out what distance you start at that gets you to land on the surface of the planet using this velocity for the initial condition. So I got to solve for my x1s and my x2s. I'm going to do it numerically. You got to have that in there. And then I have a range for times. I think 1,000 seconds is good enough. And you'll see it when I hit return. It produces this procedure right here, and it's got FKF, and this is, it's got RKF. This is the run-kutta function, and uses it for 5 run-kutta method, which is a version of the run-kutta method. And now, to see what comes out, Maple has this built-in function called ODE plot, and the way you use it is you've got to give it, you see how I stored all this information in spacecraft, so I'm going to tell it spacecraft, and then I have a square bracket. I want to pull out the t variable, and I want to pull out the variable that tells me the distance above the Earth, or above the planet. And so that's that distance right there, or the distance from the center of the planet. And then I'm going to plot it in red, and a plot style is point. And if you hit return, you're going to get a graph that looks like this. Now you notice it's curving, and it stops right here. Well, how do you know if you're on the planet? Well, that's got to go back to our radius r. And so our radius r is this value. So 6.38 times 10 to the 6. So that's what you want to remember. And if I come back to my graph, did we get down there? Don't know. Everything's in 7. This is kind of big. I'm going to restrict my t values. And I think I can do it this way. If you look at the graph down here, this is between 200 and 400, so that's 300. So let's do t at 250 to 350 and see what happens. All right, I'm closer. How about, it looks like it's turning right a little after 300. So let's get much closer. Let's do 90. And see what 310 does. Okay, I'm still there. Now, we are not getting close enough, so I don't think this was a successful trial. I believe it's gotten down. Okay, I think I can right-click and come down to nearest point on line is what I want. If I put it there, it tells me. Now it's all 10 to the 7s. Power 10 to the 7s is way too high, so I need to execute my solution a little farther up. I don't know how much farther up, because we're not, well, I should say not farther up. I need to execute it closer to the surface. Okay, we don't want it 1. How about we do 1.5 and see what happens here. So I'm going to need another return. So let's evaluate. Let's make our plot again. Okay, I need smaller time values. Sorry about that. And let's see, 1, 2. I think I could do this at 303. There we go. No. Still shooting way off. So I need to make this smaller. Let's try 2. Okay, so that seems to have worked, but my scale is not big enough to see the plot. So let's go back out to 200 and 400. Okay, I see more of a curve. Okay, let's go back out to 1,000. There we go. Still not enough, because this is 6.7 and I want 6.3. So I need, okay, that doesn't look good at all. I'm crashing through the planet there. Yeah, I'm in the surface of the planet and we're having problems. It's much smaller. Okay, so that is too short. So it's somewhere between that and 2. Let's try that value. Hit return. Oh, that's a curve. Again, crashing through the planet. So we've got to be higher up than that. Let's try 7.5. Okay. That's a little too much because I'm not getting to 6.3. So let's try this value. Okay, I need to make these smaller. It goes to 1,000 seconds. Alright, but you see the technique you can use. You can also try plotting the velocity of the spacecraft. And this is negative. We need to go to positive. That might help you figure out when you turn around, when you start going up. Yeah, I don't think we went out far enough there. Let's try a 3 there and see what happens. Yeah, getting really close. Oh yeah, we're getting really close. Let's do 70 and 9, 80. And we are a little far over because it's 6.38. We crashed through the surface of the planet. So we need to start out a little higher. Let's try that one again, and let's look at this one. Okay, so that's sooner. I don't know if that's soon enough. Let's go back to 900. There we go. Ooh, 3.38. I'm going to have to turn this down even more. Let's make this a 5. And make this 5.5 by looking at the graph. Hit return. Alright, what number are we looking for? Let's put this at 3.5. And 9.5. Hit return there. So it does go to 0 right there at that time limit. A little after 9:51. Okay, so this is how you figure out what your answer is for this solution. You get it down to where you get this number as close as possible within 1/10 of a second they're looking for. And we can get it down to 1/10 of a second by evaluating the x value in the spacecraft. If I type in spacecraft, and my time here is looking like 9, let's right click on that and do probe information. Okay, you see how small that number is? So if I put that right there. So I want 951.2. So if I put in 951.2 and hit return, see it gives me the position of the spacecraft right here, and we're looking for what value? what is R? 6.38. 6.381. So we're far into the planet a little too much because of this number right here. So we might want to blast off, start a little higher. But this is how you get to the solution. You go through these techniques. Now, one of the ones you're going to be asked to do is orbital mechanics and or Kepler's laws. And in there you have 3 equations, and actually you have 4 equations because you have x and y. And you set them up this way. You set up your initial conditions, and you can do desolve for that, and you get this nice plot like this. Okay, and you need to answer the questions the same way I do. If you call Kepler's laws at particular times, you will see the velocities. After the Kepler's law, there's a Halley's Comet one you want to do, and again, you have these differential equations, and we have to set up some parameters. I called one mu, and you get 4 equations again. Actually, you get x, y, and z coordinates, so you get a lot more equations. You have 6, but you can use the desolve command on that too, and it will calculate Halley's Comet for you and its position. You notice as it's moving faster, my method doesn't work that well, but this does a pretty good job. And then your own comet, you can do Halley's Comet. This is my own comet that I set up from what the problem declared, and I got this information. And you have to believe you had to calculate its period, so I'm plotting out its period or its position away from its center here. Alright. And that's how you use Maple and desolve and ODE plot to get information for these Maple applications.
Alright, so I hope by going through this lesson you have better understanding of how to set up a system of differential equations to be solved numerically. You have a better understanding of how to do Euler's method, improved Euler's method, and the Runge-Kutta method for numerically solving first-order differential equations. And 3, how to use Maple to solve these first-order differential equations, both writing a program or using desolve, and then how to get information from that using desolve to solve your differential equation numerically, and then using ODE plots to help you get information to determine if your numerical solution is correct, if you guessed the right starting altitude for our spacecraft simulation. And then you can use this for all the other application problems also. So that's in. I'll see you in class.